So I think that we can officially start. So once again, hi everybody, my name is Jacek, and as a member of the Meet Encode team, I'd like to just welcome you, not only from my side, but also from our partners, Hause Stiftens, TechSoup Europe, SAP, and the German Federal Ministry of the Interior, and welcome to our first Meet Encode online seminar in July. And if you're new, let's just tell you a bit about Meet Encode. Meet Encode was launched in 2017 to simply assist nonprofit organizations in providing digital skills education to young people aged from 8 to 24 years old across Europe. And now, 5 years on, Meet Encode has reached more than 175,000 of young people across 35 European countries, giving them all the digital literacy and coding skills to just thrive in tomorrow's competitive digital economy. And what Meet Encode do, like Meet Encode awards microgrants of as much as 500 euros to local nonprofits to facilitate the digital skills workshops they deliver. And I think that many in our audience today will be recipients of those grants. So good to have you here. And why have we launched the Meet Encode online seminars? This series is simply an extension of the Meet Encode commitment to help nonprofits become more innovative, more creative in the work they do. They're designed to, first of all, inspire all of you, our Meet Encode community, with multiple learnings and insights from great SAP experts and speakers and coaches in the exciting world of IT, coding, and digital skills. And after listening to last month's outstanding Meet Encode Purpose Talk with the co-creator of Snap, Jens Münich, I'm even more excited about today's seminar. We are very delighted to have an SAP coach once again with us, Jadga Huegle, returning to us today with another great seminar to explain how media computation can assist with teaching general purpose programming by playing with the ingredients of your favorite pictures, music, movies, and books, like the daily stuff. And with this topic, you'll be able to attract non-traditional audiences to your event, extend your portfolio of fun projects, and even delve into advanced blocks-based programming. So that's I think super beneficial. And as most of you probably already know from the first Meet Encode online seminar with Jadga, she was originally a biologist and discovered her interest in computer science while building a small connected greenhouse. And since then, she has become a Snap and CS education devotee and is eager to share her excitement with everyone. Jadga works for SAP Snap team and develops learning resources for schools and workshop facilitators. And we are super honored and grateful and amazed that you found the time to be with us today, Jadga. And I think it's the high time to dive into today's topic, learn more about media computation with Snap, and just have some fun. So Jadga, over to you.
Thanks, Jacek, and thanks for joining, everyone. Just right ahead, I might have gotten carried away and I prepared like way too many projects, so we might not be able to do all of them, but I will send out, or Philip will send out a collection on the SnapCloud page later on, so you can take a look at the other projects that I prepared for the workshop. And also, most of the projects that I'll show today, or that we will talk about today, are part of the OpenSAP course that I just posted the link in the chat. And if you want to take a look at that, feel free to. So it's free access. You just need to register at OpenSAP, and then you can access all the learning materials. The course is also currently running. So if you want to have a certificate, I think you have time until some point in September. And also, so that I don't forget it, I'll show you right away. Share sound, share desktop, great. We are having a conference at the end of July, SnapCon, and you are happy to join if you want to delve deeper into programming education or Snap in general, programming education research, whatever. And there, oh, I lost the chat. Chat. There you can register and find out more about the Snap conference. Okay, what do we want to talk about today? The topic that I suggested for this talk is media computation, because I personally, as Jacek mentioned, didn't start programming for quite a while. So I was 25 or something when I started programming with that small connected greenhouse. And I wasn't particularly interested in programming before. And also most kids start programming with games or something, and I wasn't much a fan of games. So I was really looking forward to also developing a new way to attract different audiences that don't like gaming, that are not the traditional math fans that usually learn how to program, to also attract them to programming. And the way we found is media computation. Media computation is something that was developed by Mark Gastile, a professor from the US. I think he's at Michigan University. Back in the day, so like 10-ish years ago, and we extended his ideas to also make them available for general purpose programming. So you can actually learn how to program by, as Jacek already mentioned, playing with the ingredients of texts, of images, of sounds. And by that, you develop a broader, let's say, digital literacy, not only regarding to computational literacy and programming, but also how does media work in a digital environment? What's it made of? How can I transform and modify it? And that's actually pretty fun. So I just wanted to show you several projects and the idea that we had while we included those projects to the curriculum. And afterwards, if we have time, you can ask your questions. If not, you can just shoot me an email later on and I'm happy to answer it. So the first project I wanted to show you, usually we start that with the Pointillism project, but I've already shown that the last workshop, so I thought we'll do something different today. And what I wanted to show you is we start with a very simple project, the random color walk, which means that we move our sprite around the stage randomly. Whenever it touches the edge, it bounces back and moves into the other direction. And while it does that, it draws its path and changes the color. Okay, so I'll, if you want, you can follow along on snap.berkeley.edu, but as I said, I will send around the projects later on, so it might be easier to just watch me doing it and then trying it yourself later on when you have the project. Okay, in Snap, you program by dragging and dropping these blocks, these pieces of code, into this scripting area in the middle. And as I said, we now want to make our sprite move across the stage. So I'll grab one of those move blocks, and we want to do that forever. So I'll put in forever loop around it. Doing it like that, my sprite will just leave the stage and I won't get it back. So great, Philip already posted the link. So we also need to include an if on edge bounce block. So let's try that again. Now my sprite can't leave the stage. As I said, we also want to draw the path it moves. We can do that by just putting the pen down. And when the pen is down, the sprite just draws everything that it moves. So this is not a particularly interesting drawing. So maybe we can change that by also adding some direction changes by just including a turn block. If I do it like that, I will just get a circle. So maybe we want to sometimes move left and sometimes move right. We can do that by just adding a pick random block here at the input slot of the turn block. And sometimes we turn by a negative number, which in this case means turning left. And sometimes we turn by a positive number, which in this case means turning right, as this is a turn right block. So we'll turn something between -10 and 10 degrees every time we move. And now we can have our sprite move around the stage and draw a random walk. As I said, it would now be interesting to also change the color. So we take a look at the color model that Snap has. So the first media-ish thing that we're going to talk about here is how are colors represented on computers. And as you might know, there are different color models. So for example, the ones that printer use is CMYK, so which stands for cyan, magenta, yellow, and key or black, which is the additive color model. And those are the basic colors in that model. Images digitally usually work with RGB, which stands for red, green, and blue, which means you mix all the other colors by combining red, green, and blue values. And the one that is often used in software that people use where they have to pick colors, and that's also the one the pen and snap uses, is called HSV, which stands for hue, saturation, and value. Value meaning something like brightness. And when you take a look at the pen color block here, you can either set the pen color to a specific color. Let's try green, and then I could draw everything in green. But if I wanted to change the color each time, I would now need to do that manually, which kind of sucks and takes forever. So it would be cool to have an automatic way to change the color. This means we have to get down to a number level where we can automatically add or subtract numbers to our current hue. As I said, we have 3 components in the HSV color model. The one that changes the hue is called hue. So here we can set the hue on specific number values. For example, I could set it to 30. Let me clear again here, which would be green, or I could set it to 0, which would be red, or I could set it to 70-ish, which would probably be blue. Yeah. And now I can also, if I'm down at that number level, I can also just change the pen hue every time I move around. So I can set it at something at the beginning. So let's set the pen hue to 0 at the beginning. And now we can change the pen hue each time that we move forward. Let's change it by 0.1, and let's include that here. So I start with the hue of 0, which is red. And now I automatically change the pen hue every time I move. And you see that the color slowly changes each time I move around. To maybe even make it look a little more smoothly, we can let it move smaller steps. And then you see that the color changes faster because we're repeating more often, or we're repeating more often for a specific number of steps. And that's an intermediately interesting project that kind of looks nice, but doesn't have to do a lot with media besides the colors. But now we can use that project to just draw on top of an image. So let me create a second sprite, which is here, that can wear a photograph of me as a costume. So as you might know from Scratch or Snap experiences, those sprites don't have to look like those arrowhead boring thingies, but they can also wear costumes, which means that I can go to the costumes tab and draw something, or just add an image, or I can take a picture with the webcam. Let's see whether that works. Yeah, okay. So now the second sprite is wearing an image of me. Let me make that undraggable and let me move it to the center. And now let's try to bring the other sprite on top of the first one by going to the looks category and clicking go into front layer. And now you can see that this sprite is in front of the stage, so we can't really see what the sprite's drawing anymore. We can change that by just making this sprite a little more transparent. So I'll change the ghost effect a few times so that we only slightly see the image, and we now can see what we're drawing on the stage. And the idea now is that we sense what's in that image on the stage. So let me call that sprite photo. So we sense what's in that photo sprite, and the color component that we want to look at is the brightness in this case. And wherever the brightness is high, we want to set the pen color to something really small so that we don't draw white parts of the image. And where the brightness is really low, so the black parts, there we want to have a really big pen size that we can see that way better. So let's try to recreate what I just said. So we need another component, which is the pen size. So we want to set the pen size relatively or proportionately to the brightness of the image that or the photo that we have here. To do so, you can sense, let me just stop that script. To do so, you can sense stuff from other sprites. So for example, in the sensing category, you have the hue add block. Let me just clear the stage again. And let me move the sprite to, for example, my face. My face should probably be a reddish hue, which means it's somewhere close to 0 or close to 100 when we click on that block now. So let me check what the hue at myself, in this case, the sprite is here, and it's 1.2, so a red color. Here in the background, we have something which should be blue. So that's the image behind me. There, the hue is more like 60-ish. We can also try my green pullover. There, the hue is that, okay, the computer thinks it's yellow. So the hue is somewhere here, 14. So that's that. So this seems to work. We can now also try that for the other components. So for example, my headset is pretty black, which means the brightness should be pretty low. So if we're measuring the brightness at myself now, it's just 14. If we measure it at the wall behind me, which is white to gray, we should get a way higher brightness. So let's try that now. And it's 70 here. So this seems to work. And we can now use that block as a reference to the pen size. So as I said, we want to have the pen size smaller at positions where the brightness is higher. So we need to define an initial maximum pen size, and we then subtract something based on the brightness from that value. So I'll grab a subtraction block, and let's set the, sometimes you just need to try that out later on. Let's just set the initial pen size to 5, and we want to subtract the brightness, which is 100 at a maximum. But if I subtract 100 from here, I will just get nothing all the time. So we probably need to divide that by something. So let's just divide the brightness by 10 maybe, and let's check that out. So if I click here now, the brightness was around 70. 70 divided by 10 is 7. 5 minus 7 would be minus 2, so I wouldn't see the pen here. If we move back here, the brightness here was 13. So 13 divided by 10 is 1.3. 5 minus 1.3 would be 3.7. So I would see a drawing here. And now let's just try that. Let's see what happens. I add that here, and we just we see now that our sprite is mostly not drawing because it's too bright, and here where my eyebrows are and where my hair is, so where it's a little darker, it starts drawing here where my hair is again, where my pullover is, and we can now do that way faster by just adding the turbo mode. And now you can see that parts of the image are drawn and other parts aren't, and the ones that are intermediately bright are drawn with way smaller pens than the ones that are darker. Let me make this photo completely invisible so you can see it better. So we could now just experiment with those values a little more. So we could set the maximum value to something bigger, or this factor we're dividing by to something smaller. But this is the general idea. So you can recreate an image by just having one of the color components left. In this case, we took brightness. And this is, by the way, also a technique that was used in newspapers back in the days. It's called dithering. And the concept of setting the pen size proportionally to the brightness was the idea behind that technique. So let me save that project. Oops, need and code. And let me create a new project where I already prepared a block for the, oh, wait, let me do that differently. I already prepared a block for the dithering part, which is a grid. So the idea behind the grid block is that it creates a grid on the stage. This is how the block looks like. I can specify the number of rows that I want, and then I can specify what action is supposed to happen in each of those cells in the grid. We can just try it with creating a grid with 10 rows. and then drawing a dot at each position. Drawing a dot in Snap means putting the pen down, moving 0 steps because drawing requires a motion, and then putting the pen up again. And to see it better, let's set the pen size to 10. Okay, so if I click that on that script now, you see that I get a grid with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows, and the columns are just calculated accordingly. It's 0.3 times the number of rows because the stage is 4, 2, 3. So we did that automatically, and now we can use the same idea that we just used by measuring the brightness and setting the pen size accordingly to the brightness with a photo again. So let me create a new sprite and let's add a photo again. And let's move that to the center again and make it undraggable and also make it transparent right away. We can set the ghost effect to 100 right away. And now let's change our script here. So we still want to draw dots. We might need a little more rows, but we can adjust that later. And we might want to clear at the beginning. So whenever we start, we want to start with the fresh stage. And now we need to add that part that sets the pen size according to the brightness of the photo again. So let's grab a set pen size block. And also we need a hue add block again. So we want to measure the brightness and not at the mouse pointer, but at myself, meaning the sprite. And now we need to combine that again, as we did the last time. So we set an initial pen size. What did I write down here? Nothing. Okay, so let's just try 10 maybe. We can experiment with that a little later. And then again, we want to change, we want to subtract the brightness divided by, let's try 10. And let's add that to our script. And now you can see that we get differently sized dots. So this one is where my head is, where my headset is. This is where my jacket is. But as you can see, it's kind of hard to see the image like that. So maybe let's just increase the number of rows that we have here. Now it's 20. You can see that, oh, I forgot to clear before. You can see that my face or my head gets visible a little more. And here also the images on the wall behind my back. Let's increase that even more. Let's try 50. And now you can kind of see it. Even the dots might be a little too big now, but now you can also see my glasses and my hair and where I'm wearing stuff and where I'm not wearing stuff, my headphones. So this already looks like me. And now let's create an even bigger number. And there you can see that we are too dark now. So we need to decrease the pen size here. Let's try it like this. So it's not that bad, actually. And this is how images were made back in the days when newspapers tried to create grayscale images, but only had black and white. So white being the color of the paper and black being the only printing color that was available. And you can still create pretty good images by just having that one color. And you can fake the grayscale by just having differently sized and overlapping, non-overlapping dots. And this technique is called dithering. So also what we found out now is that most values like color, hue, brightness, and whatever are represented as numbers. So let's check out how text works on a computer next. So this was the image part or the first image part. And now let's check out how text works. I'll save that project as Meet and Code. And I'll share those later, as I mentioned. Okay, let's create a new project and let's take a look at sounds, at text. To work with text, there are different blocks in the operators category, and the ones that we want to look at now are the Unicode off and the Unicode as letter. Unicode is a concept of representing texts or characters digitally, and surprise, it's numbers. So usually the Unicode is hexadecimal numbers, but for readability and also usability with younger kids, we just convert that to decimals, so it's easier to use in school. Also, I mean, not just in school, it's just easier to use. And here you can see that, for example, the Unicode of the lowercase a is 97 in decimals. The Unicode of uppercase A is 65. Let's try J for Jadga, which is 74. So you can also try other signs, for example, which is not part of the Latin alphabet, which would be 196 then. Or you could try space, which is 32, or exclamation mark, which is 33. So this is just a way to represent stuff, characters as numbers. And also the other way around, you can of course input numbers here. Let's try, I don't know, 294 and see what happens. So this is this interesting character, or we could try 300, which would be this one. So you can use that to then create characters from numbers again. And I prepared something for that. So here I made a project that can encode text as colors, because now that we know colors can be numbers and text can be numbers, we can just transfer the one into the other. So the idea behind that project is that you go somewhere to the left of the stage and then put the pen down. And then for each item in that totally secret text that I wrote down here in this variable, I just set the pen hue based on the Unicode of that letter. As you know, colors only go from 0 to 99, or the hue only goes from 0 to 99, but the letters that we just saw start at, so the letters that we normally use in Latin alphabet start at 32, which is space, and end at lowercase z, which is 122. So we just subtract the Unicode of space, which is 32, from the Unicode of the actual letter that we're just looking at, and then we move 15 steps. So what this does is it encodes my totally secret text as colors. And now we want to read that text back. So let me just check the chat. Yeah, right. So Ascii is also a way to digitally represent numbers, to digitally represent characters, but Ascii just contains less characters than the Unicode does. So Ascii also is the same idea. And now we want to read that back. So the idea is the same as last time. We just measure the color component here, in this case, the hue, and then we move forward and just transfer that back to the letter using that Unicode block. Okay, let's try that. So this seems like a good place to start. So maybe let me just check what the position here is. It's our y position, so it should be 0, and the x position is minus 197. So we start by going to x minus 197 and y 0. So this is how our decoding script starts. And then as a next step, we want to measure the color component at that position, and then we want to move forward afterwards. So measuring the color component, we do again with the hue add block. So we grab the hue block and we want to do it add myself again. So in this case, it's 45. We only have like full number Unicode, so we need to round that number before we can keep computing it. So the rounded hue at that position is 45, and now we need to think of the we subtracted 32 when we encoded the thing. So now we need to add the 32 again, so we have the right color in this case, or the right Unicode value. So let's add the 32 here, or let's add the Unicode of space as we did here. So now we have the right Unicode, and now we can report that Unicode back as letter. So this is the letter of this first color slot here, and it's a capital M. And we can just say that for a second or so. Let's do 0.8 seconds, and let's just say that. And now we want to do that multiple times, of course, so I don't want to move it by hand all the time. So we can automate that by just moving the 15 steps that we had here again afterwards. Okay, now I can click like until we're done. That works as well, but we can also automate it by just repeating it until the saturation is 0, because when we're back here on the white stage, we have a saturation of 0, and then we can stop because we know that there are no letters coming anymore, because space, as you recall, also is a color. So you can basically see the spaces because they are the 32 minus 32, 0, which are all the red spots here. So let's do it as I just said. We repeat this script until the saturation that we measure with that sprite is 0. Here, the saturation at myself is 0. Okay, now let's try that. And you have to, I'm just saying it, so you have to read it. And we get MEET, so meet, and code, so meet and code is awesome. Awesome. So we get meet and code is awesome, which is surprisingly also the text that I encoded, which you can see here. I hope no, probably you can't. Let me just show it here. So that was the text that I encoded as colors here, and now we decoded it again. So you can also use that concept to just do smaller quizzes and stuff, have secrets encoded, and then let the kids decrypt those secrets. And the idea behind that is, again, the encoding part. So as I already mentioned, we encode things on computers in numbers. So we encode colors in numbers that represent hue, saturation, value. We encode text in numbers that are represented by the Unicode. And the idea behind that is, how did that work? It's something that's called the data information knowledge pyramid. It's not a pyramid here, but if you're at the number level, you're here at the data part. So data doesn't mean anything because you just get the numbers. What makes the numbers interesting is the context. So if I have data and I add a context, I can then get information, which is what we just did. So we added the context on how to interpret that data. Once we said, this is numerical data, but we want it to be colors, and then the computer knows what to do and encoded it in colors. And then we said, oh no, now we want the numbers to be text. So we encoded it in something different, or added a different context, and then our numbers were text. So this is a really important part to understand. What you get on a computer is just data, and it doesn't mean anything when you don't have the context. So this context part that you need to add is what makes information on a computer and basically everywhere. Okay. So let me just check the okay, chat for a second. Okie doke. The next project I wanted to show you is that this also works with other encodings and modifications. So it's just a video because I'm really, really bad at whistling, but Jens also has a version of that project where he transfers the frequency of his whistling into colors and then transfers it back. So I would now just share that video with you for 2 minutes, because as I said, I'm unfortunately really, really bad at whistling. Okay, can you maybe, if you can't hear the sound, let me know in a second.
Let's try it.
And here, as you can see, the idea is the same. We set the pen hue based on the microphone frequency, and then we transform that a little bit so that it fits in the right color spectrum or in the right number spectrum that we need for the color range. But the idea is the exact same. And now let's see how he decodes it and whether it works.
Okay, let's stop it. So now we drew something with colors. Should we try to play it back? Let's try to play it back. The key for this is the add block. The add block gives me the hue at, for example, the mouse pointer. So in order to get the frequency at a certain mouse pointer, I just need to reverse the scaling I did. So I'm going to say I'm going to multiply it by 20. And I'm going to add 700 to it. And this should be the frequency. Now I should be able to play this frequency. And I want to make this interactive. In the same way that when I'm pressing the mouse the mouse key, I want to play this frequency. Otherwise, I don't want to play anything. Okay, let's do this forever. And let's check it out. I'm moving the mouse. Now I'm pressing the mouse pointer. Pretty neat, right? We can also click on anything.
Okay, I think that's enough for that. So you see, this also works for other things, not just text and color, but also for sound and color. And of course, I could also somehow transform sound into text if I wanted. So this is how you can transform different forms of data into each other when you add different contexts. Okay, the next thing I wanted to look at with you is, now that we know how things work in general with numbers, we might want to analyze them a little closer. So let me, did I save that project? Yeah, I did, I think. I didn't save that project. So let's save that. Need Encode, color code. Okay, so let me create a new project, and let's take a closer look at sounds. So we have a block in the sound in the sensing category that lets you access the microphone. So for example, the microphone frequency or volume. Let's just try volume. If I don't say anything, the volume is 0. If I talk a lot and try to talk really loud, the volume increases or decreases when I don't talk that loud. And we can also take a look at the samples. Sounds digitally work with samples. Let me just record a sound for a second. Meet and code. Meet and code. Okay, and let's take a look at that sound. For example, we can look at its duration, which is 2.88 seconds, or we can take a look at its sampling rate, which means the number of samples that are recorded in 1 second, which is 48,000. So I have 48,000 samples in 1 second of sound. And we can take a look at the actual samples. So the samples of my recording are values between -1 and 1 when I record them with the microphone. So here you can see that they are different. And we can now also analyze live samples from the microphone. So I can click here, and then I get a list with 512. Okay. I hope you could see my screen before. This list has 512 elements, which is just the last 512 samples that my microphone recorded. Let me try that again while I'm talking. So now you can see that we have different values between -1 and 1 again. Someone raised his or her hand. Can participants talk here, Jacek? Or could you just ask your question in the chat, maybe? Then I can try to answer it.
Yeah, not in this mode. But we have one question on Q&A mode.
Okay, yeah.
It is, what does Unicode do? What is the purpose? And does it use Ascii system?
Okay, so the Unicode basically is an exchange for Ascii, I think. So the Ascii code was the one we used before, but it contains way less characters. They also are encoded a little differently, and I don't know the exact differences, but they serve the same purpose of encoding characters in numbers. And usually today you use Unicode because it has a way bigger set of characters. Okay, so Gabriele, maybe you could just ask your question in the chat and then I can try to answer it later. So we can take a look at the microphone samples, which is, as I said, the last 512 elements of our microphone that it recorded. And we can now try to plot those by just trying to see how they work and how different sounds work. We can plot them by just drawing every one of those samples somewhere on the stage. So let's start by going to the left of the stage, which is -240. And we can go to the center here on the Y direction or Y position. Our sprite is now here. And now for each of those microphone samples, we just want to change the Y position based on the value that we have here. So for each sample in our sample set, in our microphone samples, let's rename that to sample. We want to do something. And what we want to do is we want to go to the Y position of the sample. But as I said, those are just values between -1 and 1. We also might to multiply it with a factor so we can actually see the differences. Because if we just plot -1 and 1, we won't see anything except a super small line. So let's just multiply the sample by 150 or so. And in an X direction, we also need to make sure that we fit all of those 512 samples on the stage. So let's just create a variable for that, which I call step. And that step, we can just calculate by dividing the width of the stage. Off is here. So we want to have the width of our stage, which is 480, by the resolution of our microphone, which is currently 512. So it's the length of the sample list. Where did I take that from here? So the microphone resolution, which is the 512, as I just mentioned. And now we, of course, need to also represent that in the motion to the right. So the X position that we have in each step is the previous X position plus the step that we just calculated. So let's try to add that. Our previous X position that we were in plus the step that we just calculated. And now let's try to draw that, which means we have to put the pen down at some point. Let's just put it down here. This now takes quite a while, and I probably started it while the microphone didn't record anything or I didn't say anything. So this is a little bit boring. Maybe let's just do this all the time and let's draw it really, really fast. So we can draw everything in one step by just including it in the warp block. So the warp block basically makes everything that's inside it in one step, and if it's too much, in as little steps as it can. So let's just add all this inside the warp block. Let's clear again, and let's try to draw this again. So now you can see that I got the line right away, but still we can't, now I did something new. Now you can see that we probably also want to do that all the time, so we can measure the current samples all the time. So let's just do that by wrapping a forever loop around that. and try to see what happens now. So we're looking at the, oh, come on. You can see that we now have overlapping all those samples that we're measuring. And now we need to add one more thing, which is just add a clear block at some point. So for example, we could add the clear block here. And now what we made ourselves is a little oscilloscope with which we can record the sound that, or which we can plot the sound that my microphone is receiving. So those are the samples from a microphone. And now we can try to, I grab my ukulele here, and now we can try to see whether we can see any difference between, for example, how my voice looks like when I talk, or how the ukulele looks like when I play it. So let me just play one string. Okay, now let me try to sing something. So I can try very low with a very low pitch. Wow, Apple Music even thinks I'm playing music. I take that as a compliment. And what you can see now is that the louder I speak, the bigger the amplitude gets. So the Y value, so the actual value of the sample represents the loudness or the volume of the sound, the amplitude. And then also we have different frequencies. And what those frequencies mean, we can now take a look at. Let me just stop that and let me create a variable. And I'm trying to make noise now. So I'll make a variable which I call noise, and I'll tell you that we just saw what we want to do now is we want to synthesize the sound. Here we had 100,000-ish samples between -1 and 1, and this is just a list. So let me create a noise variable and let it be, I set it to an empty list. And now I have my noise variable here. And now I just randomly want to add, let's say 48,000, because that's 1 second, samples between -1 and 1. So I repeat 48,000 times. Oh, that's just 4,800. And I want to add stuff to the noise. And what I want to add is a random number between -1 and 1. So we also get decimal numbers. We need to start by -0.9999, whatever, to 1. Oops, not 10. Let's do it again. If I do it like that, it takes forever until we get to the 48,000. So let me wrap the warp around here again. So, okay, here we got it, 48,000 samples between -1 and 1. And now we can play that sound or that noise with the play sound block. I can just add those samples here and let's see what happens. Sorry, I should have made it a little less loud. Anyways, so this is called white noise. You create it by just having full spectrum, which means from -1 to 1 samples randomly selected in your sound. But as I said, one important component for audio stuff is the frequency. So if we make random noise, but not 48,000 of these, but just maybe 48, and then we repeat those same 48 randomly selected samples 1,000 times or 100 times, let's see what happens then. Okay, so we create a new variable, which I'll call samples. And again, we want to set that samples variable to an empty list. Empty list. And then we want to add stuff. In this case, maybe we want to add 100 samples randomly. So I'll just duplicate that here and exchange this noise for the samples. If I play that sample, those samples now, it's just a super small white noise. It's just a really small clicking sound. But as I said, we can now extend that by just adding those same samples over and over again. So let's do that by repeating, I don't know, let's just do 100 times. Also, let's add a warp. And what we want to do is for each sample of the samples list that we just created, we want to add that sample to a new variable that we call sound. So we set sound again to an empty list. Oh, well, I didn't want to do that. We set sound to an empty list so we can create a new list of samples. Or let's just do this 48 times maybe. So we can, for each sample in the samples list, we want to add that sample to the sound. Okay, let's do that. Oh, that's 480 times, sorry. So now we have two different lists with 48,000 elements. One is the noise. Careful, I'll play it again. And now we want to try to play our sound, which is still a short white noise, but repeated 480 times. And now let's see what happens. We have made ourselves, or we have synthesized ourselves an actual sound with a 480 hertz. So we could have tried 440 anyways, which would be the A. But this is the idea of frequency. So repeating a small amount of samples over and over again, you can create different sounds with that. So let's try to make one more, and you can see the changes in the frequency. So let me make samples 2, and let's just duplicate that script. And let's set samples 2 to a list, and let's add stuff to samples 2, but maybe just 50 times. And now we want to do that as well again. So let's also create a sound 2, and we want to 960 times add each sample from samples 2 to sound 2. And here again, we have, oh no, I killed the sound. Okay, let's do this again. Okay, so here's the sound, 48,000 elements. Here's sound 2, 48,000 elements. But the initial data that we made sound from had 100 samples, and the initial data we made sound 2 from had just 50 samples. So now let's try to listen to both sounds. This is sound 1, a sound. And now let's try sound 2. So this one has a way higher frequency, it's actually 1 octave more, because it's just half the number of samples. So double the frequency. And this is how you can work with frequencies and sound samples. So now we only have 4 minutes left, and I wanted to share one more thing, which is actually my favorite. So I'm trying to talk super fast. Let me just save that project. Sound. Because the really interesting thing about Snap is that you can also use it for advanced stuff. So we have some blocks which are called higher order functions, and one of them is map. A higher order function is a block that takes another function as an input, which goes in here, or produces another function as an output, which we don't have here. So map, for example, works like this. If you put a function here at the beginning, you can then apply this function to a whole bunch of data to a list. So let me create a list here, maybe 1, 3, 5, 8. And now I can, for example, take this whole list times 2. So the map blocks works as follows. For the first time, the first element of the list goes into that empty input slot, and the result is reported to another list. Then the second item, then the third item, until the whole list is done. So what I get here is a new list where the result is 2, 6, 10, or 16. and 16, so the function applied on every element of that list. This is a super powerful tool because the cool thing is we already found out that everything that we worked on so far is on a number level, and we can just apply functions on any type of data. So this works with text, this works with sounds, and so on and so forth. This also works with images, but I won't show that today. So now let's take the samples of the sound that we just recorded. So I don't have it anymore. Wait, we need to record it again. Meet and code. Meet and code. Okay, so here's our recording. Here are the samples of our recording, which is a list that we can apply functions on. And for example, one function that we could apply would just be we divide every element by 10. So let's play the original sound. Meet and code. And now let's play this new sound that we made. Meet and code. And you see, we divided every sample by 4, which means we decreased the amplitude, so we just made the sound more quiet. We can also add other functions. So for example, the abs function, which you can find here, just reports the absolute value of each of the elements, which means we don't have any negative values anymore. Let me also just import a library real fast, because we then can also plot the sound. So let's plot this first. Let's plot the original sound. So this is the original sound, and this is the sound with the abs function. And you can see that we all lost all negative values. And if we play that sound, meet and code, it sounds very nasal, and you lose some of the information. Also, we could, let me do one more effect, which I like a lot. We could also, this is a little complex one, we could also create an echo by just averaging some of the samples with some previous samples. So averaging means that we want to divide something, and we want to add something. And what we want to add is the value that we're currently looking at, so the value, and we want to average that. Let me move that here. And we want to average that with a value from some time back. So we take this item block, and we want to average it with the item index, the current index, minus 5,000. Also, let's see if this works. And sure, of course, we need to divide it by 2. So again, what we did here is we built an average of our current value and the value we had 5,000 samples ago. And for the first 5,000, nothing happens because we don't have the index minus 5,000 there, and the rest will get averaged. So let's play that sound and let's see how it, or whether it works. Meet and code. And you see that you can, this was even a little hard, that you can create an echo effect by that. Meet and code. And again, what I want to say here is, once you're at the number level and once you understood how those media is represented digitally, you can use those map functions, and there are other higher order functions to do anything. The technique is the same for all types of media, and you can transform them as you wish. And also the techniques work for other types of data. So once you're at the number level in other data, so for example, in that OpenSAP course, we also take a look at Passengers of the Titanic or Dungeons and Dragons spells or different things. You can apply the same techniques over and over again and get great results. So that's what I wanted to show you today. If you have questions, I do have 5 more spare minutes, so feel free to ask them now.
Thank you, Jadga, so much. I need to repeat myself, but it was super inspiring, and especially for a non-programmer like myself, it was super interesting. And I really enjoyed the message that you shared with us, that data without context cannot be information, and so on and so on. That's super nice. And as we're running almost out of time, if you have any quick questions to Jadga, that's your time to ask them. So you can do it by chat or a Q&A section. We have 2 or 3 more minutes to finish up today. Let me just remind you that the recording of the workshop will be available on our YouTube channel. So if you want to go back to anything that Jadga said and do it once again, or write something down, feel free to do it. The video should be up in like maximum 2 days, let's say. So okay, so do we have any questions? I think that you were so specific and detailed that people
I probably was so overwhelming.
So far have nothing to...
I will create a collection later on, and I think Philip last time sent around an email afterwards, and I will add the link to that collection there. And I mentioned that you can apply the same techniques also to images, because images is just numbers arranged in a table. So I will also add a project for image manipulation there, which you can check out at home later then.
Okay, so if you don't have any more questions to Jadga for now, I hope that she will be back to our online seminars with Purpose Talk series once again in the future. So you'll have your chance. As for now, I just want to thank you, Jadga, so much. Another webinar with you, another super interesting topic, and the way that you explain things, like, it makes me excited in coding, despite the fact I'm not a coder, but it's super, super nice. And also a big thanks to you guys, our Media Code audience, for your time and attention. We have enjoyed hosting you, and I hope that you walk away with a feeling a bit more inspired and motivated to code, to program, and to dive into the digital skills world. We look forward to seeing you again at the Media Code online seminar. So just please remember about checking our website and social media profiles to stay updated and get the information about future seminars. And as for now, thanks again. Have a nice day. Enjoy your evenings, and see you soon.